Hi everyone. This is the sixth week of the course. We have still one more week to go next week. Today we are going to work with OpenStreetMap, learn how to get data from OSM, and also we will perform also some simple network analysis. But before that, today, if we have time, I will also talk about the final assignment because the timing is a bit bad. It overlaps with the holidays. I thought if I share it already now, you're going to start working, so you don't have to stress about it over the holidays. But yeah, so at the end, if we had time, I will go through it in more details. But for now, I can say that the information about the final assignment is already published on the course's website. So you can see the topics. So there are basically 3 topics you can choose from, and you also have the option of choosing whatever you want to do as long as you do enough, and the criteria for enough is described on the course's website. You can also come up with your own topic, but there are a few topics we have suggested here that you can choose from. You can use large language models, AI, if you want to. Just be transparent with that and tell us how you have used it. One more important thing is like we did the exercises weekly individually, but for the final assignment, you have the option of doing it with someone else. So you can have pairs if you want. It's optional. So if you want to do it together with someone, you can do it. But the second person, like one is the driver, so you can choose who submits the actual assignment. But the other person also has to submit a short report, like reflecting on what has been done to make sure that everyone has been involved in the process. So both of you have to submit the assignment. But yeah, we can revisit this at the end if we still have some extra time, but there's information here, how it works. Yeah, so let's start with today's materials. Yeah, so as I said, we will be working with OpenStreetMap. Personally, for me, this is like one of the most practical lessons. Like very often I have to actually come, if I need this, I would come to this course's website and check how this is done. Yeah, getting data from OpenStreetMap, you know probably OSM is a very rich source of data. It's crowdsourced, so there are a lot of people contributing to the OSM from all around the world. It's a good source of data depending on what you want to do. And in Finland, generally, we have a good access to many types of data set, but it's still in some cases, some things, like the quality of data is quite good, what you get from OSM. So you still need to do it. For example, in Finland, we have like DigiRoad, which is a very good collection of like road network from all the country. But it's still in some things, like for example, for pedestrian roads or pedestrian routes or cycling routes, OSM is sometimes even better in some areas. So anyway, it's nice. And generally, for access, there are a number of ways, and we will see how you can access data from OSM. But the typical way is through the API of OpenStreetMap. So they have documentation, and you can see how you can connect to OSM via the API and then get the data you want. But again, we are doing this course in Python. We are comfortable with Python. We have access to GeoPandas and all the libraries that we have been working with and we are comfortable with. So it's nice that there's a library called osmnx, developed by a researcher from, I forgot the name, but Boeing from California, I guess. So he has developed and he's very active with like improving the library all the time. So it allows us to stay within Python environment without worrying about how to work with the API of OSM and get the data within Python, so you don't have to worry about the API. So that's what we are going to use in the first part of the lesson. In the second part, we will perform a simple network analysis. So we will try to get the shortest route from point A to point B. And for those of you who have done network analysis before, you know it's a bit annoying process. Like if you're doing it in software like QGIS or ArcGIS, it's a bit annoying. It's much easier actually to do it with Python, especially if you're trying to make a loop and repeat it for many origin destinations or many individuals. So this is quite nice and practical, this lesson. So Yeah, so in the first part, we will retrieve some data from OSM using this library. Then we will extract simple street network properties and statistics. We will see how we can do that. And then we will perform a simple route optimization in the later part of the lesson. So a little bit about OSM. There's a link to the wiki page of OSM so you can learn more, but it's a huge project. There are a lot of contributors from all around the world. So it's a very big project. And since it's crowdsourced and they have a good cause and it helps many people in many situations, it's good to contribute. So if you have something to add, it's encouraged to add geographical data to OSM and contribute. OSM has more than 8 million registered users who contribute around 4 million changes per day. And this was checked like 2 years ago, so it should be still pretty valid. But you see, it's a very big thing. The database is huge. The database contains more than 7 billion nodes. And again, this is from 2 years ago, so probably it's more now. Yeah, we already used OSM a couple of times for smaller things, more basic things. So one of the things we used it for was geocoding, was it week 3. We used it for geocoding, so you use Nominatim, which uses OSM for geocoding some addresses. And last week we used it in our static maps when we were, well, in our maps as a background. So we used OSM as a background to our static and interactive maps. So we have seen it before. Yeah, so now we are going to learn how to work with this library. As I said, the community behind this library is quite active, so they make updates quite frequently, and they have a good documentation. So if you're unsure, we see a few examples today, but there are a lot of details, so you can always refer to the documentation. And the author of this, the main developer of this library, has also published a paper based on what they have done back in 2017. So if you're curious, you can check out that article. Yeah, so we will get some data from OSM. In the second part, we will perform network analysis. And for that, we are using, there are a number of libraries for doing network analysis. So there are many of them, and they use different algorithms, different ways of finding, for example, shortest route between 2 points or multiple points. NetworkX is one of the popular ones, and it's quite basic. It's not just for network analysis. It's actually meant for graph analysis, so it's a mathematical thing. So it's used quite a lot for mathematics. But of course, networks are graphs. So what we do with graphs is it works for analyzing, like for performing network analysis as well. So this is the library that we are going to work with. So let's open CSC Noppe. If you haven't pulled the latest changes yet, please do now. I have already done it, so I have 2 notebooks here. We will start with this retrieve data from OSM notebook. I have started this, yeah. Okay, so we start by importing the library. Let's run this. Cell. Just got an error. You probably get the same thing. So I noticed this earlier, but I deliberately didn't fix it, so we can fix it here together. When working with Python programming languages, you should be able to handle such errors. So can you guess what's the problem here? When we were trying to import the osmnx library, we haven't done anything else. We just got this error. So if you're doing this on your own computer, where would you look for the problem? No, this is an open library. Yeah, so the problem here, like if you just look at the traceback, well, the problem has happened when importing. It has tried to import topological error from Shapely, and there you have gotten an error. So this kind of errors, well, you're importing osmnx, but you're getting an error about Shapely. So these are like dependent libraries. OSMNX is using Shapely as one of its dependencies. So there's a mismatch here. So what has probably happened is that Shapely has been updated, for example, but we are using an older version of osmnx. So you can check. From the terminal, I want to check. So I'm checking the version of my Shapely library. You can do it for any library you want. And you can see that this is 2.06. So you can Google and see what is the latest version of Shapely library. I want to also check what is the version of osmnx I'm using. Yeah, so with osmnx, we are using 1.1.1. And I searched this earlier. Actually, now there is a version 2 of this library release. So we are using a new version of Shapely, but an old version of osmnx, so leading to this problem. So what I'm going to do, if you're doing this locally on your own computer, of course, it's different. But now we are working on CSC, so the idea is the same. So I'm going to use this, uninstall the library, and install a newer version. And you can do it directly from your Jupyter notebook. So this is something you might need when you're doing your final project. There might be a problem with some library, or you might want to be adventurous and try some new library. So this is how you install, uninstall libraries. So first I will uninstall what we have. So if you want to use it normally for installing libraries or uninstalling, there are two channels. There are more, actually. You can use pip or conda for installing libraries. If you want to access it from Jupyter Notebook, you have to put an exclamation mark at the beginning. So what I'm going to do is uninstall the library that is causing us problem. It was osmnx. So I will uninstall the library. I have a typo here. Yeah. So now the library was uninstalled. So I want to install it back. So by default, if you don't specify what version, it should install the latest version of the library. So I will change uninstall to install. And it installs you the library. So now you can see it installed osmnx version 2.0.0. This has happened because I made this environment for this course 2 months ago. So apparently a new version of this library has been released since, causing the issue. Yeah, just to be sure that everything works fine, let's restart our kernel. So we install, and I removed that y at the end, dash y. Okay, so now restart your kernel and run this cell. Hopefully, yeah, so it works well. So now the problem is resolved. So if you encounter such issues, it's pretty easy to fix. Yeah, okay, so now that we have imported our library and library seems to be working fine, let's start by getting our data. So I want to get my data from a place. And one of the nice things about this library, osmnx, is that it uses nominatim geocoding library, not geocoding mechanism system. So if you want to fetch data from a certain area, you do not need to know the coordinates of that area, which is nice. You can just say, I want data from Helsinki, I want from Kamppi. You just give the name of the place and it does the geocoding for you. So instead of providing a coordinates, a pair of coordinates or an area, I will just provide the name of the area from which I want the data.
I'm sorry, I still get an error trying to install.
What is the error you're getting?
Cannot import name graph simplification error from osmnx error.
Okay, let me look at what you have. Did you uninstall it first?
Yeah, I can try it again.
Yeah, uninstall it and remember to reset the kernel.
Oh, yeah.
Yeah. Yeah. But did it work for the rest of you? So the area from which I want to get the data is compy. You can type it however you want, but be specific enough so the geocoding can find the place. So this should not go wrong. Compy, Helsinki, Finland. So what I'm trying to do now is to retrieve network data from compy area. And I'm going to store my data in a variable under a variable named graph. So this is how you can get network data from osmnx, like from OSM using this library. So there is a function called graph from place. So osmnx dot graph from place. And the only thing you need to provide is the name of that place. You have already stored this under a variable. So I'm just going to copy the name of the variable and paste it here. Let's just run this. So this might take a bit of time depending on how big the area is, how heavy the data set is. So if you try to get this for whole Finland, it might take minutes or even longer. So yeah, so this works quite well for smaller areas. If you have very large areas, we will see later what are the options for you. But for compy area, it works fine. It took less than 10 seconds for me. So let's see what we got as the output. So as usual, I'm going to check the type of the data we just received, type graph. So we can see that we have a new type of data that we have not seen before, and that's a multi-graph, which is it is a NetworkX or osmnx object type. So this is something we haven't worked before. So it's not a GeoPandas yet. So if you want to make it a GeoPandas and do all the things we have done during the past few weeks, you have to still take a few steps. If you want to learn about this object more and the attributes it has, there's a link here you can follow and check later. But now we want to visualize it quickly. Of course, we will see later on that we can convert this to a GeoPandas and geodata frame, and then we can just visualize it the way we have done it, like for example last week. But if you just want to quickly see what you have, this library itself has a function that allows you to just quickly visualize what you have received. So it looks very similar to what we have done previously with matplotlib. So it returns a tuple of figure and x. You have seen this in the previous course, which allows you to control some of the features of the visualization. So I'm using, under osmnx, there is a function called plot graph. And then as the input, you provide the name of your graph. So just note that this is a function, not an attribute. So what we do with attributes, like when we use with GeoPandas, when you want to plot, you put the name of your geodata frame, dot plot. So it's an attribute of the geodata frame itself. Here it's a separate function. So I'm accessing the function from the library. And then as input, it takes the name of the data, the name of the variable in which you have stored the data. So in practice, it doesn't make a difference, but just note that this is a function. So yeah, so let's just run this and see what we get as the output. That worked very quickly. You can see this is a network. For those of you who are familiar with compy area, you might recognize the shape, but this is the compy area in center of Helsinki, and this is the road network. As you can see, it consists of points or nodes and edges or the lines representing the streets. So this was a quick way of just visualizing to see what you have gotten from OSM. But if you want to like work with it, analyze, do things, then you probably prefer to just make it a geodata frame and then use all your knowledge from working with GeoPandas library. So this is what we are going to do next, converting our graph to a geodata frame. So there is a function for that returns a tuple. So it returns two values, the nodes, the points, and the lines. So that's why I'm providing two variable names to catch both of what the function returns. So I'm getting nodes and edges. So this is the function we can use to convert our graph to a geodata frame. So the function is called graph _2 _ GDFs, which is probably short for geodata frames. And then provide the name of the graph, which was graph in our case. So let's just run the cell. So now that we have a geodata frame, so let's just look at nodes. So I'm just using the good old .head to take a quick look at our data. So now you see it's a geodata frame, so it's just a normal geodata frame we have worked with. And these are the first five rows of our data. So you have the coordinates, you have some information about the nodes, the points. We are going to explore those other attributes a bit later. Let's also look at the edges. So similarly, these are the lines. So in the first case, we got points. If you look at the geometries, those were the intersections, the nodes in our network. And here we are getting line string because these are the streets, so these are lines. And again, there are some attributes, for example, what kind of road it is, how many lanes there are, what is the maximum speed. So depending on where you get the data from, different countries, it's a bit different, like the tags, the information. In some places it might be correct, incorrect. Well, it's crowdsourced, so there is no guarantee. But yeah, it comes with a bunch of attributes, which is nice. So now that it's geodata frame, so if you have gotten your data, if you want to do further analysis, you can just do what you want. So it's a geodata frame. So now let's try something else. Now we learned how we can get network data from OSM. Next thing we are going to do is to get a polygon. So if you want to get the polygon, the border of Helsinki, the border of Finland, if you want to get any polygon using a place name, we see how we can do that. So let's get the area of Kamppi. And there is a separate function for doing that. So from osmnx, there is a function we are accessing. It is called geocode to GDF. So as you can tell from the name, it takes the name of the place and it geocodes it and returns it to you. So if it is represented as a polygon in OSM, you get a polygon as the output. So I'm just going to use the place name in which we had Kamppi. Let's also run the next cell, check the type of area. So it returns a geodata frame to us, so there is no need to convert anything. So if you use that geocode to GDF, as you can guess from the name, it takes the name of the place as input and returns a geodata frame to you. So if it is point, it will give you a point. If it is an area, it will give you a polygon.
Tells me that data is not defined in the sample.
What is not defined?
Area is not defined.
What have you put? Did you put place name here? Or?
Maybe it took some time. Yeah, okay, no.
Okay. Yeah. Okay. Okay, so let's take a closer look at what area it has. So we only got one polygon as output. So it's just one row of data, and that, well, it's the polygon of Kamppi area. So the output is just one object. let's plot it and see what it looks like. It's a geodata frame, so you can just use .plot attribute. So area.plot. And this is the border of Kamppi area in Helsinki. So now we want to get more data. As I said, OSM is very rich, so there are all kinds of data. And if you want to make, well, you can always check OSM, see what kind of data is available, and then they have all the documentation, so you can see what is available for use. Now we want to try and get the building footprints from this area. That is, for example, a data set that is very often useful because it may not be available in every place, at least not for free. So I'm going to create a new variable, call it buildings. And I'm going to try a new library that will get feature data for us. So it's called, under osmnx, it's called features from place. So for everything we are getting, there's a function. So if it's a feature, if it is a area, if it is a network data. So it's might be a bit hard to remember what function you have to use, but of course that's why we have documentations. So features from place. The first thing you need to provide is the name of the area from which you want to fetch the data. So I'm going to get my data for Kamppi again. The second thing I'm going to provide is the right tag. So if you check the OSM tags, it's a very there's a lot of information there because there's so many different types of data and they have different tags. But one of the tags that OSM uses to represent buildings is building. So they have tags and they have also sub-tags. So building is a kind of feature in OSM, but there are also different kinds of buildings. So there are like sub-tags. So if you want to provide that sub-tag, if that's a word, you can just provide it here. So it takes a dictionary as the input. But if you want to get everything, you can just set this to true. So I'm going to get everything for now. Later we can specify what kind of buildings exactly we want. Okay, data was fetched. It took just a couple of seconds. Let's run the next cell to see how many rows of data we got. So it got 450 building footprints from Kamppi area. Let's take a quick look at our data using .head. So this is what the data looks like. So we have some information. For some of them, we have the street address. For some of them, you see it's missing values. Some of them have name and some information, but it is missing for many of them. Yeah. Do you have this comma at the end, or is it building, not buildings?
Buildings first, and then it's building there.
Yeah. And don't you have a typo in the name of function, features from place?
Yeah, it points at the what do you say, double dot of the building.
Okay, let's take a look. It's a dictionary. Yeah, put brackets. You should put this curly bracket.
Okay.
Yeah.
The same thing.
Yeah, it's hard to see from here actually. Yeah. Yeah, so this is a dictionary. It has to be like this curly braces, not normal parentheses. Yeah, so this is what we got as the output. Yeah, so if you check the documentation, there are different kinds of buildings. For example, you can set building to school. Then it will give you all the buildings which are marked as a school in the database. Or buildings true. It used to be yes. This is not correct, actually. We should update it. So it used to be like you can set building to yes, but now it's true. So that's what we did to get everything that you have with all tags. So yeah, so now we want to get some points of interest. So we got buildings now. We want to now try and get some restaurants. So let's map the restaurants in Compi area. So we are going to use the same function, features from place, and this time we are going to use another tag. Again, to learn what tags you can use, you have to check the documentation of OSM. So I'm going to get restaurants and name it just restaurants. And I'm going to use the same library, which was the same function, which was called features from place. Again, I'm going to provide the name of the area. And then I'm going to provide a dictionary. So this time I'm accessing some other tag. So many places are marked under, like services are marked under a tag called amenity in OSM. So I'm going to get the amenities. So again, there are many subtags, what kind of services you want to access. What I want to get is the restaurants. So there's a tag for that. These tags are generally consistent, but they might be slightly different in different countries or different places. But generally, they should be consistent. Yeah. So at the same time, I will print the number of rows we get as the output. So 160 places are marked as restaurants in Compi area according to OSM. So again, here, if you wanted to get all services, all amenities in Compi area, you could have just put true instead of restaurant. But we put restaurants, so we only got the restaurants as the output. Okay, did I skip something? Okay, actually the code was typed in down here. I just read it. But anyway, let's just run this. Yeah, so again, you saw earlier with buildings that it comes with many columns. So let's check some of the columns. Well, let's check the list of the columns that come with this data. So with amenities, you can see that you have the address, you have the city, country, house number, what kind of cuisine it is, and a number of information that might be useful. Well, data is not always very complete, but there's a lot of information there. So let's select some of the useful columns and print them. So I'm just keeping the name, the opening hours, the city, country, house number, postcode, and street, just to show you how it works. And then I'm just printing the top 10 rows of the data. So yeah, so these are the columns we kept. So we have the address, we have the postcode for some of them it's missing. And we have the house number, country, and so on. Yeah, and this is OSM is crowdsourced. So if you see a restaurant that you frequently visit and the data is missing, of course you can just go and edit the data. And because it's crowdsourced, there can be mistakes in the data as well. So next thing we are going to get from OSM is the parks and green areas. So I'm going to use the same function, features from place, and get a number of things. So this is an example of how you can access different tags at the same time. So if you want to get green areas, again, you have to check documentation. So you have to be careful. So some of the parks are tagged under leisure areas. But if there is a grassland somewhere, that is under land use. So if you want to have green areas that includes both parks and like grasslands in Helsinki, in wherever, then you have to be like careful. Again, you should check the documentation. We did this earlier, and we know that parks are under leisure. And so if you want to get it at the same time and just combine them, then in your dictionary, you can just provide them both. So from leisure tag, I will get the parks. From land use, I'm getting grass. So let's just run this.
So does this mean that we only get the features that have both?
No, it's like union. So we take both and it will be combined. Yeah, yeah. Yeah, so we got both of them. We combined them. We stored them under parks. So let's see what we get as the output. Again, some of the columns, name of the place, and a bunch of information. And this is what we've filtered on, based on. So leisure, park, there should be a column somewhere there, land use, grass as well. So yeah, so at the same time, you can access several tags. You don't have to write it separately. Of course, you can write it separately and combine them, but you can do it at the same time. So the output is a geodata frame. So if you want to visualize it more nicely, you can, of course, do that. So I'm going to plot it. So parks.plot. And this time I'm going to apply a color to it. You can choose whatever color you want, but since it's green areas, it makes sense to use some shade of green. So this is the data we got. So these are the parks and grasslands in case there were any around Compi. Yeah, so this is our data. Next, we want to just plot our data a bit better. The code is already typed in. This is what we learned last week. So it's just plotting and adding different, just assigning different colors to everything. Yeah, so now we just created a nicer map. We colored the buildings as gray, green areas as green, of course, and then we have the dots, the nodes that we got from the graph as yellow, and we have adjusted the marker size, and we have applied some transparency to some of the layers like buildings and restaurants. Yeah, so this way we created a nicer looking map. So let's take a few minutes and practice this for another place. So do this, check your understanding. Let's do it for a few minutes, then we continue. So just try it for any area you want. We tried it with Compi. So just try it for your own neighborhood or whatever area you're interested in and see how it works. Then we continue. Okay, so
probably have to reinstall this.
Yeah, you missed the beginning. Yeah. So yeah, pip uninstall. Uninstall it first because the library has been updated. We're using an older version which has a conflict with Shapely.
Then probably install it one more time.
It didn't install because it asks you to say yes or no. in command prompt it's okay, but here it's difficult, so that's why it would put a space, dash, no, like the dash, like this one, and y. So you already say yes, so it doesn't ask you again. So run this again. Yeah, you might need to reset the kernel first and then try it again. Yeah. Okay, now run that cell. Yeah, run this. There shouldn't be any space between y and. Okay, so now you installed. It was version 1.1.1. Now you can reinstall it. So just edit this one, remove the on, so it becomes installed. And you can remove the dash y as well. Okay, now can you scroll? So now you're upgraded to version 2. So just restart your kernel and yeah. Thank you. Oh. So one thing about installing and uninstalling libraries is that with CSC, Notepad, the environment we use, every time you open a new session, things are wiped out. So next time you run this, you will probably get error about osmnx again. So if you're using this again, remember to do this. So, but if it is on your own local computer, of course, you wouldn't have this problem. There's also a way of like, so it's the same. If you're doing your final assignment and you need a library for it, the next time you open a session, the library will be missing. So you can just reinstall it. There's also a way to install it in a way that it stays. I can share it with you later, but it takes a few steps. But most things you need are already installed, so you shouldn't need it so much. Okay, so did you manage to make a new map for a new area? Ah, okay. Yeah. Okay, so I see some of you have created some nice new maps. So you learned how to work with this library. So, but at least for one of you, it seems to take long. I don't know how big of an area you use, but you will see soon if you want to do the same thing for the whole Finland or a very large area, depending on what data you're getting. For example, street networks are usually very large data sets. So if you try to get the whole network, street network of a whole country, then it might become very slow. Of course, if you have time and if your computer doesn't crash, then it's fine. You can just wait to get the data. But if you're working with really large data sets, if you want to do network analysis for whole Europe, if you want to see how you can drive from Tallinn to I don't know, Barcelona, then probably going with this library may not be the best option because it takes quite long. So for very large data sets, then of course you can access the API of OSM. That's one way. There are also these data dumps. So there are places where they gather like data in large amounts and they just dump them into a website, to a database that you can download, and they are like updated on a regular basis. So one of them, we have a link here. It's geofabric.de. So they regularly fetch data from large areas, so you can get the whole data from Africa or a continent. So you can just download it, and this, as you can see, the sizes can be quite large. So in this case, it's like 25 gigabytes. So if you try to get these 25 gigabytes through this library, it may not work so well. So in those cases, if you need from a very large area, a large amount of data, there are similar services that you can use. And the data usually comes in a certain format. Like in this case, it's a PBF file. It's actually the OSM's own format, so it's a protocol buffer. So it's very effective, efficient for very large amounts of data. Yeah, so in case you end up using these huge data dumps, then there's a library in Python called PyROSM that works nicely with this data format. So if you ever needed this, remember there are Python libraries that allow you to work with this data format. But for most of our daily uses, this library is more than enough. Yeah, so in the next part, we are going to do some network analysis. So we will continue working with the OSM, and we will get the route between 2 points. So let's start. In the first part, we are doing the same thing as we did last time. So I'm getting the graph data, so the network data again from Compi. But here you can see that you can specify also the type of network, and again for the exact wording, you should check the documentation. But using network type, you can specify what kind of road network you want. So if you choose bike, it gives you the bicycle routes in Compi area. So this I've gotten from the documentation to see what is the right tag used. And then the rest we have seen before. So we are just using graph from place. Place name is Compi. The type of network is bike. And then we are quickly visualizing it. So let's run the cell. Okay, so this is nothing new, similar to what we have, except that these are the bicycle routes. So one good trick, so of course you can just start, now you have your network data, you can just start doing the network analysis. But one good trick is that, well, if you're getting, if you have a smaller area and you're getting the route between 2 points, it's a good idea to apply some kind of buffer so you get your data for a bit larger area. Because if you are, for example, going from this point to this point, because you don't have data from here, it will just give you this as the shortest route. But there could be a road here that lies outside Compi area. That's why you haven't gotten it. So if you're getting network data, you want to do network analysis, it's wise to get a bit larger data. So we already have the area of COMPI, but now we want to apply a bit of buffer to COMPI area to get a bit larger data set so that the network analysis works well. And this is what we are going to do now. So I will get the polygon of COMPI. This is something we already did once, so it should be easy. So I will get it and name it as place polygon. And the function's name was geocode to GDF. And then you provide the name of place, which we have already stored under place name. Okay, so now we want to apply a buffer. But one thing we have to be careful about, that this data is coming from OSM. And we remember from last week that it is using the Web Mercator. And what is in Web Mercator, the coordinates are in what unit? They're in degrees. So if you want to apply buffer, unless you exactly know how much it will be in degrees, it's a bit tricky. So if you want to apply a buffer of 1,000 meters, you have to calculate, okay, well, how much is it in degrees? Probably not the most practical thing. So what we will do here is we convert it to another coordinate system that is metric, and then you can apply the buffer. So you can just say 500 meters or whatever buffer distance. So now I will just take it to another coordinate system, and I will store it in the same variable. So place polygon. Here I have a typo up here, yeah, place polygon. So then I'm using the 2CRS to take it to another coordinate system, and I'm going to use the coordinate system that we use a lot in Finland. That's 3067, which I know uses meters as the unit. Now that it's in meters, the coordinate system is, now we are in a projected coordinate system that uses meter. I'm going to apply the buffer, and this is something we have already done in the first week. So I will access the geometry of my COMPI polygon. And then I will apply a buffer of 200 meters. You can, of course, try it for different, the radius can be anything you want, but 200 meters should be enough for our area. So now that you applied your buffer, remember that you want to take it back to the coordinate system we had, because we want to do network analysis. And network analysis is going to work with OSM, and OSM is in Web Mercator. So remember to take it back to the CRS of Web Mercator. So again, I'm going to take place polygon to the original coordinate system. And the coordinate system, the EPSG code for it is 4326. Okay, so do we all know what happened here? So we got the polygon. We wanted to apply a buffer. It was in Web Mercator, which uses degree. I took it to a metric system. I applied the 200-meter buffer, and now I'm taking it back to the original coordinate system. Here I have a typo. Don't repeat my mistake. So yeah, so the rest is just converting it to a new geometry, and that's it. We visualize it. So let's run this. Hopefully we don't have any typos. Yeah, so now we got the data for a bit larger area. So if you compare it with the first one, you got a bit more because we applied the 200-meter buffer around the polygon. So let's quickly look at our data. So now we are getting the, so this is our data. Now we want to get the roots. So we are not, you remember last time we tried to get the network, the graph was returning us a tuple, so edges and nodes. Well, you don't need nodes in this case, you just want to see the lines. So if you specifically want to get the edges and not nodes, of course you can get it as a tuple and just use edges. But if you don't want to get it at all, then you can just set nodes to false, edges true. So this will not return a tuple anymore, it just returns individual value. So in this case, we will only get the edges. So let's just run this and also take a look at our data. Yeah, so this is what we get. This is line. So we only got the edges of our data, not the points. We don't need the points right now. So it has a number of columns. Again, it's hard to remember what is what, but this is from the documentation of OSM. So there are different columns like bridges. It's a Boolean, so is that segment a bridge or not? So it's true or false. Then you have the geometry. Then highway is the tags for roads. The type of road is stored under highway, which is a weird name. But anyway, so the type of highway, so it doesn't necessarily have to be highway. It's just different types of road are stored under the tag highway. Then you have number of lanes, the length of the segment, the maximum speed name, whether it's one way or not. So there are a number of information. Two columns that we will get back to shortly is U and V. So each segment, each of these edges has a starting point and an ending point, and these are those nodes that we did not get. So this U and V correspond with the ID number of those points, and we will see them later. We will use them later. But this is what U and V represents. So let's see what types of a street does our network comprise of. And there is a, so let's check the values under highway. As I said, the type of the road in OSM is stored under the column highways. So let's look at that column and get a value count from it. So you can see from our compy area, well, compy plus that buffer, we have roads that are tagged as service roads. We have 981 segments of them. We have pedestrian roads, residential, cycleways, and primary, secondary, unclassified. So these are the values that we have in the column called highway. Yeah, so now we want to work with the coordinate system again. Well, as we saw already, this uses Web Mercator, which is not, which is in degrees. So what we want to do, we wanted to take it to a projected reference system that works with meter. So there is a library within, and we can do this directly within this library. So there is a function called project underscore graph. And what it does, you can check the documentation, but it takes the coordinate system to a UTM that is suitable for the area. So even if you don't, so you know, transverse Mercator is a projected coordinate system and it is in meters. So it's still in this like this global coordinate system, but it is in meters. So if you use this function, project graph, it takes your graph data to a UTM that is suitable for your study area. So it's smart in that way. So if you're doing it for Finland, you do not need to specify which UTM you need to use. So if you just leave it blank, it takes it to a metric UTM. A UTM is metric that is suitable for the study area. Of course, you can just say that specifically for UTF for Finland is like Yep, so it's like TM35, so you don't need to specifically mention. So it's smart in that way. So here I have added this try and accept, because if you run this multiple times and if you have already done the projection, you will get an error that this is done. So with this try and accept, I'm just avoiding this error in case you run this cell multiple times. Yeah, so we are using this to take graph to transform into that UTM that is suitable for our study area, and then I'm getting the nodes and edges again, and I'm checking the CRS of our nodes. So now you can see it's a projected coordinate system. This is not Web Mercator anymore. This is the code for the UTM35N, which is suitable for Finland area. So yeah, so you can just do it from osmnx graph to GDF project underscore graph, and then we got the data again. So now that we are in meters, it's a bit easier. When you're doing network analysis, speaking of degrees is difficult, doesn't make so much sense. So now we can look at some of the properties of our network. So you can look at some of the basic properties using basic underscore stats. And then you provide graph as the input. So it gives you a bunch of information like the average length of the segment, what is the total length of all the road segments in your data, number of counts nodes in your data set, and street lengths, total street lengths, average segment count. So there's a bunch of statistics from the graph data that you have retrieved. So it also can give you density. So it tells you how many nodes there are in your data, or it tells you how many segments there are. But it doesn't tell you much unless you know how big the area is. So you cannot compare. So if you compare the number of road segments in Kamppi with, I don't know, some other neighborhood in Helsinki, it's not a fair comparison because that other neighborhood might be just bigger. You cannot conclude that we have more roads in Kamppi. So we can provide an area and then it calculates the densities for us. So what area do we use? Now I'm applying a convex hull. So I'm doing a union of all the roads, and then I'm applying a convex hull on it. So let's just run this. Yeah, so you get a warning that this is changing. So this used to work in earlier versions. Now it's still working, but if you use a future version of this library, you might get an error because it is going to get deprecated. So the new thing, it already tells you you should use unary union instead. So this is how we would do that. So let's just already use the new method. Union underscore all. And then I'm applying the convex hull. Yeah, so that line of code is will be deprecated soon. So this is the new way of doing this. So we get the union of all the road networks, then we apply a convex hull, this polygon around it. So now I can use the area of this polygon to calculate these basic statistics again. So remember, last time we did this far, we didn't provide an area, which is optional value. This time I'm also providing the area, which is the area of my convex hull, the one I just calculated. So as area, you can use whatever makes sense in your case. In our case, it's easy to just apply a convex hull. You could have used the area of Kamppi, for instance. So now you see the statistics list is a bit longer. You also have density-based measures. So it gives you the node density per square kilometers or intersection density per kilometer. So yeah, so if you provide area, which is optional, it also measures some density-based calculations for you. Okay, so now that we explored some of the basic features of this library, now let's get to the main point, which is to calculate the shortest path between 2 points. Of course, you can try this for whatever points you are interested in, but here we have an example. So this is the address for a startup hub in a former hospital area, somewhere there. And this is a park. And for those of you who are locals, you know that this is a nickname for this park. The official name of that park is something else. But when we are using nominatim, it's smart in that way that it also might know the nickname of the place. So yeah, so the nickname works well enough here. You could have also put the official name or the address of the place. So we are trying to get the shortest path from this place to this park. So of course you can provide, here we are using nominatim, so it just geocodes get the coordinates, but of course you can just enter the coordinates also manually, but we are not going to do that. We are just going to use the name of the place and just use the function to geocode it. So the code is already typed in. Let's just quickly go through it and see what we are doing. So we are setting the origin point, which is this Maria 1 in Helsinki. We are getting the location using this function that we have already used a couple of times today. Then we are transforming it to the UTM to work with meters. This is again something we have done. Then we are accessing geometry and getting the centroid. So it's an area. So if you're getting the park, it's a polygon. How do you calculate the distance to a polygon? You have to have a point. So you can use whatever point. In this case, I'm just getting the centroid of the polygon. So if you have a building and you want to get the distance to the building, you have to have a point. So in this case, it's just convenient. I'm getting the centroid of that polygon. So I'm doing the same thing for both of them. First is the origin, and then I'm repeating the same thing for the park. And I'm getting the centroid of the park for convenience. So let's just run this. So now the origin and destination is defined. As I said, you could have alternatively just use the coordinate systems, but coordinates of the points. But it's nice to work with geocoding. It's easier. So now we have the geometry point. We have the points are defined. We have the geometry object created that represents the origin and destination locations. So now what do we do? So when you're doing network analysis, essentially what you're doing is a graph analysis. And for that to work, you need to be somewhere on the graph. So if your point is not exactly on the line, it's not going to work. So what it does, it snaps, like when you use ArcGIS or QGIS to do network analysis, if your point is somewhere and there's a road next to it, it always snaps the point to the closest road segment. And then from there you can get the address or get the route or the distance or whatever. So we are doing the same thing here, but of course we are programming, so it's not automatic. You're not automatically snapping to the road. But there's a function that makes this easy for us. It gives you the closest node to your point. So remember, we had the roads, lines, they had nodes. So now I want to see this Maria 1 is closest to which node. And from that node, I can do the graph calculation and do the network analysis. So this is what we want to do. And we get the ID of that node. So origin, so I will store the ID in a variable called origin node underscore ID. And as I said, this library has a function specifically for that, and the function is called nearest nodes. So these are the nice things that this library does for you. Otherwise, you had to come up with a way of getting that. So from my graph, and then you have to provide the coordinates of that point. So we have already gotten this, so we have the geometry. So I'm accessing, from origin, I'm accessing the x coordinate. Again, I'm accessing the y coordinate. So as input, it takes your network data, which is graph, and the coordinates, x and y separately. And since we already defined the geometry, it was easy to get the x and y. So that's all you need to do. I also put the name here so we can quickly look at the output of this. So it gives you the ID of the node that is closest to your origin point. In the second cell, let's just run it. We are repeating the same thing for our destination. So we have the ID that is the node, the ID of the node that falls closest to my origin and destination points. So now I know from what point on the graph to what point I can do the network analysis. So now we are ready to do the actual routing. So now that we have that, there's a function, again, we saw so many functions today, that does this shortest path analysis. So let's just store the output under a variable called route. From osmnx, this is the name of the library, shortest underscore path. So as the input, as you might guess, we need to provide the graph data that we are working with. And then what it needs is the origin and destination ID. And this is what we calculated up here. So it just wants the ID of those points. So you cannot directly provide the coordinates or your own point. You need to first get that node ID that is closest to your point. Origin node ID. And the other one was destination node ID, destination node ID. That's all you need to do. Let's also put the name of the variable here to see what we get as the output. So this is the output. This is your shortest route. It doesn't look like a route, but can you guess what this is? What are these? It's a list of numbers. What is this list? Yeah, so this is the shortest route, but it doesn't give you the road segments. It gives you just the nodes that are along the way. So do you have any idea how we can get the route from this?
Well, the edges were defined by origins.
Yeah, so that's one way. You can just use that U and V columns we had in the data. So that's one way of doing that. Here we are going to take a shortcut, make things a bit easier. So what we are doing, we have these points along the road. So what we can do, we can apply a polyline. So we can recreate the segment. So it saves us a few steps. So now we have these nodes. We are going to apply a line, a polyline on these nodes. So let's go and do it this way. So let's visualize. Again, if you want to let's run this first. So there is a function called plot graph underscore route. And it's nice. It can highlight a route on the data, on the network. So instead of getting the route and visualizing it and applying a different color, if you just use this, provide the graph, the route, and remember the route is just a list of the nodes. So it doesn't even have to be lines. It just highlights it for you. So this is the shortest path from that point A to point B. So we got it already. We can visualize it. The next thing we want to do is to save it as a geodata frame. So for that, we need to take a few steps. But already now we can see that this was done. We have the output, but now we want to save it to our disk, like make a local copy of that. So now I'm going back to my nodes data set, and I'm selecting the ones that are along this path. So remember, we have a route, we have a list of all their IDs. So I'm going to use that list and use this lock that we are familiar with from pandas to get those selected. So these are the nodes. So I'm getting the full column, the full rows from the original nodes, using that list I got for the shortest path. So these are the points we are working with. So now we can apply a line string. So this was the easiest way to create that line. So from this set of points, I'm creating a line string. So let's just run this. This is something we have done several times, starting from week 1. So this is a line. So we just recreated the line that the shortest path between the 2 points. Now that we have the route as a line string geometry, then making it a geodata frame is easy. Again, this is something we have done a few times. So what I'm doing here, I'm just getting the routes, the geometries of the routes from here, and the route line, and then I'm getting the nodes added as a column. I'm setting the right coordinate system. I'm using the same coordinate system as the edges, the original data we got from OSM. We are also getting the length. So if you want to calculate the length of the segments, you can just do that using the geometry.length. So let's just run this and see what we get as output. So now we ended up with a geodata frame, which only has one row, and that makes sense because it's just one route, and we changed it into one line string. So now it's a geodata frame that we can just use it for our analysis. We want to make a nice visualization of this with some added elements. So we want to also have the buildings added to make a nicer looking map. So this is something we have done before. Let's do it again. Let's get the building data from compy area. So I'm just setting building to true to get all kinds of buildings regardless of their type. So now I'm visualizing. The rest is what you have seen before. So I'm using just matplotlib, applying colors, transparency, and using a base map. I'm using the CartoDB positron that we used last week to create a quick visualization. So this is what it looks like. So we colored the roads as gray. We highlighted the shortest route, and we added a base map. So one thing you haven't seen before, you can apply line style like this. So if you put 2 dashes, it will just show it as dashed line. So there are a number of things. If you check matplotlib documentation, you can see what other values you can provide here. Probably can put dots and asterisks and so on, but you can check. But at least dashes work nicely. If you put double dash, it will dash the line. So we can see the shortest route highlighted nicely here. So now that everything is ready, let's just check the data one more time using .head. Looks fine. So here we are taking an additional step. Well, we are saving our data down here, and the code is already typed in. But if you try to save it now, you will get an error that some of the column values are not supported. And these are the columns that are problematic. How do I know it? Because I've run this before, I've got an error. So I'm handling these columns separately. And the reason why you get error is that these columns return lists as value. So if you have list of IDs, list of things, it's not an acceptable value for a GeoPackage or geodata frame. So have you ever seen a shapefile in ArcGIS or in QGIS that has a list as value? You might see it as a string, but not as a list object. List object is for Python. So these are lists. So when you try to directly store a list as a value in your geodata frame, you get an error. So what I'm doing here, I just identified these problematic columns, and I identified it, like I tried it, I got an error, then I just added it to this list. And I'm converting them to a string. So they will still look like a list, but they're a string. So I just put them into quotation mark, kind of. So does this make sense? So later on you can try. Just do not run this cell or remove some of these columns. When you're trying to save, it tells you that this is wrong type. GeoPandas doesn't accept list as data, as value. So I'm just keeping the value as it is. I'm just converting it to a string, so it won't be a list anymore. So GeoPandas will be happy with that. Yep. I did the same thing for the nodes, and then saving. So saving is simple. You just define the path, and we save our data. So we are creating just one geo package called osm_compy, and then we are adding several layers to it. So streets, route, nodes, and that's it. So if you want to also store the building data we just got from OSM, you can do that. So now it's saved. If you check under data folder, it should be there. So 3 seconds ago, we created this geo package with all these layers saved in. Yeah, so there are other libraries. NetworkX is quite popular. There are also other libraries for working with graph analysis. So if you are curious, you can just Google. There's one example mentioned here. But this is not the only way to do this, but it works nicely and works nicely with that osmnx library. So this combination works nicely. Yeah, do you have any questions? If not, we have like 10 minutes, so we can look at the final assignment and what we have to do for it. Just one reminder, this Friday is a public holiday here, so we do not have the exercise session, and we don't actually have an exercise this week, so you can just relax over weekend. There is no exercise, but next week we are working with raster data, and we have an exercise next week. So this week there is no exercise, so you can just relax. But since some of you joined a bit later, because the deadline for the final assignment is after the holidays, and I decided to share this with you already now. So if you have time, for example, this week you don't have exercise, so you can already start thinking about your final assignment. And over Christmas, you don't need to worry about doing your homework. So yeah, so the final assignment, the goal is to practice and demonstrate the skills from, most of us have started this course already from first period with GeoPython. So now it's the time to shine. Like we had in the first period, the project was a bit simple. Here it's a bit more advanced, kind of. So whatever we have practiced and learned during these 2 periods, now we can show off your skills in this final assignment. So the objectives is like 3 things, and you will be graded basically based on this criteria. Data acquisition, so we have learned how to get data from different sources. Like today we worked with OSM, we have worked with like reading local files, we have seen WFS, like we will learn about raster data next week. So you will acquire data from some source. You will perform some data analysis. We have done like map overlay, different kind of analysis during this period. So you try some of those, and then of course you visualize, which is a big part of GIS, of course. As I mentioned at the beginning, you can use AI, large language models, but of course be reasonable. The whole thing cannot be made with LLM, large language models, or AI, and it will be quite obvious if the whole thing is produced by AI. But if you use it, just tell us how you have used it, to what extent you have used it. Exercises were done individually, but for your final work, you can have a pair, so you can do it together with someone. If you do the exercise in pair, well, one of you will be the driver who submits the code and everything. The other one still needs to submit a short report, so it can be a PDF, just tell what you have done in the project. So the idea is that both of you know what has happened and you have done the work together. So yeah, so there's more details on the course's website, but you have to submit. So it can be a MD file, or it can be a PDF, and it has to be submitted on GitHub. So similar to weekly exercises, there is a link to accepting this one. So you accept it, you will have a repository which is almost empty. So you just do your work. If you are the driver, submit the code, the whole assignment. If you're not the driver, then just mention who was the driver, who was your pair, and submit the report. So it doesn't have to be super long, just short report telling what you have done. Pay attention to the documentation. So be careful with this. Most of you do very good work with coding, so you solve the problems very nicely, but some of you are a bit sometimes you don't take documentation very seriously. And that is bad because, well, first of all, it's part of the grading. So if you do an amazing job coding, but you don't have documentation, you will lose the point for documentation. But also it makes it very hard for us to understand. So imagine you're going through the submissions of 30 students, and you might have very smart solution. You have solved something in a very smart way, But just looking at your code quickly, I may not see that. So if you have documentation and you explain that, okay, I solved this in this way because of this and that, not only I understand your code better, but also it makes your assignment like more properly done. So to take it more seriously, so we can fully and correctly understand what you have done. And it's of course a good practice that we have been emphasizing during these 2 courses, to have documentation for what you do. The documentation can be like as code cells like you did in the first period. That's the easiest way. If for whatever reason you prefer to have a separate documentation, you can create an MD file and write your documentation. And for documentation, of course, you have to explain what you have done, what are the libraries you have used. You may end up using another library. Sometimes some students have done that, like you want to do something extra and you install a library. So mention that. So if I'm running the code and it needs another library, I should know and install that library. So documentation is important. As I said, you just submit it over GitHub, accept the assignment, you will have your own repository. So one thing is that in the MD file, in the markdown file of the exercise, let's see if I can quickly show you. Yeah, so in the MD file, there is a place where you can mark whether you're done with your assignment or not. And the reason is that you will be working, because we have 2 deadlines, I will tell you soon. So this is our way of knowing if you are done already. So here, so once you're done with your submission, remember to check this one, submitted. It's the MD, it's this README file. So when you check submitted, then we know you're done. We already start grading you. Then you get your grade more quickly, which is what most of the students want. Yeah, so remember to do that once you're done. Another thing is that if you end up working with large data sets, GitHub, if you have the free account, well, GitHub is not a place for storing data. That's not a good practice. But anyway, it has a file limit of 100 megabytes. So if you end up using a data set that is 1 gigabyte, you cannot store it there. So just provide the link to the data, or try to use WFS or something so you don't need to download the data. And it also makes it easier for us to grade you, because we don't need to download your data. So try to use online sources and not download the data. If you really have to have your own local data, then just provide us with a link to your data. But yeah, so we have this 100 megabyte limit on GitHub. So the deadlines, we have 2 deadlines. One of them is the last day of December. The other one is 6th of January. Yeah, so we start grading you in order of submission. So if you want to get your grades more quickly, just submit it quickly and earlier, and we will grade you. And 6th of January is the cutoff threshold, cutoff deadline. And the reason is that I will be on leave from mid-January for a while. So if you submit like end of January, actually there won't be anyone to grade you. So probably you want to submit in time so you get your grade in time. Yeah, so the idea, so you can choose your own topic, and I will talk about this soon. I will try to wrap it up in 2 minutes so you can go. But yeah, one of the ideas is to create some kind of urban indicator. So you can create your own urban indicator, something related to population or street connectivity or something. So you can just be creative. Of course, you can read literature, see examples of different urban indicators, and do it for wherever you want. You can do it for Helsinki, Tampere, your own city, town, wherever you're from. So that's not a problem. Yeah, so just pick one urban indicator and do the analysis. These are examples. There's accessibility, green area index, population distribution, demographics, street network metrics. So the idea is that you just do some mathematical calculation. You get your data, do some mathematical calculation, data analysis, visualize it. That's one idea. The second idea is spatial anonymization. So this is more on like shapely geometry level analysis. And the idea is that you create a random point data set. Imagine these are home locations of individuals, and you want to anonymize it by displacing them. So you just randomly move the points to some direction. So you just manipulate the X and Y coordinates. So this is the second idea. So this is more on the shapely level. And of course, you visualize it and So that's one thing. The other option is your own. Yeah, the first one I actually skipped was accessibility visualization. So we worked with this travel time matrix from Helsinki, which was developed in our digital geography lab. So we have worked with the CSV files before, those grids. So the idea here is to create some kind of tool that allows the user to just find the files. You remember there were so many CSV files to choose from. So a file finder, it has table joiner tool, so it automatically joins the tables based on the ID values. It visualizes it and does some kind of comparison. So this is another idea. And your own topic. So if you have something interesting, you can just use whatever data you want. And remember that if you go with your own topic, make sure that you have these elements in your work. So you get your data from somewhere. So data acquisition, one thing. Data analysis, we have learned a few things during the course. Try some of those. And visualization, it can be interactive or static or both. And yeah, so, and there are some tips and tricks. I will upload this slide to the course's website. So remember to follow the good coding practices that we have talked about a lot during these two courses. And remember to check this checklist. Follow the main structure, the recommended structure. Be careful with documentation. Visualization is needed, so put some effort, produce good maps. And test your code. If you're designing a tool, try it with different inputs to see if it works fine. And avoid unnecessary repetition. So write a good code that doesn't repeat itself. For example, by writing functions, then you don't need to repeat the code. And make sure that what you do is sufficient, especially if you come up with your own topic, then just make sure you do what is required. Yeah, so there's more detail on the course's website. The feedback is not open. I usually show this on the last week, so that's why this is here. But feedback will open next week. So once it does, remember to provide us also with feedback. But that's it for today. If you have no questions, then we can finish here and continue next week.
Do we have next week another meeting?
Yeah. Next week we have a normal week. We have lecture on Wednesday. It's about raster, and we will have exercise. So the last exercise is exercise 6. Lecture is lecture 7, so don't get confused. Lecture 7, exercise 6. This week there is no exercise.